All right, so yeah, it's me this week, and I've got such a pleasure to be presenting this particular thing to you. It's a massive shame that I'm not there in person, because in my office I have the thing. It's a textbook, a famous textbook, and it would give me great pleasure to slam it down on the table because it's enormous. I was actually looking around to see whether I had a book here at home which was similar sized, and I literally don't. So let me introduce you to this absolute marvel, which is known as Numerical Recipes. Okay, just by a quick show of hands in the, or put your hand up or whatever, who actually has heard of Numerical Recipes? Good, how many? Okay, all right, so here's what it is. As they explain their, note there's 4 authors here, just before I move on. As they explain their reasoning, what they wanted was to present practical methods of numerical computation, which can be simultaneously efficient, clever, and clear. Starting in the 80s, what they wanted was just a very straightforward presentation of various methods of dealing with numbers in a computer, various sort of mathematical problems that you would try to solve with a computer. And what they wanted to present was numerical recipes, just a straightforward way of here's how to solve it, here's some code which will actually do it. The problem that was arising was a lot of the methods on paper were sort of written by mathematicians, and so sort of as rather terse and complicated. And a lot of the computer code was sort of hidden in black boxes. There were sort of big libraries of computer code coming out, but they were very hard to get in behind the scenes at. So they published, these 4 authors published this book to try and lay things out in as practical a way as they could. I should note 3 of them are astrophysicists or were astrophysicists at some point in their careers. So this is very much a let's get on with it and just help me solve the problem I have, rather than sort of mathematicians who are interested in or computer scientists who just want to provide all the details. So first published in 86, there are first and second editions that have all the book, as I'll show you later, has code in it to really give a practical, here's some code that'll actually do the thing that you want it to do. There were versions, they were trying to guess which language they should do it. So they produced versions in Fortran 77, Fortran 90, Pascal, Basic, C, and C++. They also note in their introduction they were entirely unsuccessful in ever predicting which language would be the dominant one in the future. The third edition is in C++, although online someone has written a version of the Java, of the codes in Java, if that's helpful to anyone. I've never used Java. And there's also ways to call the code from Python and MATLAB. There's a bunch of stuff online. Importantly, this book, I've got the version from the library. There's actually 2 copies up there. I got the big one so I could slam it on the table. So it's, again, big disappointment I couldn't do that for you. I might just walk into the student room tomorrow and do it anyway on everyone's desk. 2 versions there. The whole thing is free online at numerical.recipes. They just nag you, they call it a nag, about why don't you subscribe, but if you're willing to wait, I think it's about 3 seconds for a PDF to load, you can get it all online. Here's how you use it. For me, and I think for most people, it's the first resource for understanding a numerical method. So it's not necessarily the last resource. As I note, the most recent version was 2007, and better methods may have been published since then. But you just won't find them in this book. And it's not necessarily for the code they provide. Often, when you look up a method and you understand the method, you can then find that someone's already coded it up for you in just about any language you want, in Python, in NumPy and SciPy, in MATLAB, in the GNU scientific library. There's almost certainly someone who's written it up for you already in whatever language you're interested in. So it's very good as a first resource for understanding. The code is good, but it just might not be the best thing out there. And there might be just a better method entirely. So the way that it's organized is that as you go to a particular topic, and here's the topic that actually Nick presented last time, how you do least squares, how you do curve fitting. So you go to chapter 15. This is from the website, actually, not directly the book, modeling of data. And the first introduction and the first chapter just try to explain the mathematics to you in as basic language as they can. They then go on to specific topics where they try to lay out for you, again, as basically as they can, the actual method that they're going to use to solve the mathematical problem that they've set up. And then written down in the book or online, they have actual runnable code that you can use with comments and, little comments all the way through that will actually run. Now, it's written in C++, so if you know C++, you'll be able to understand what's going on here. If you don't, then that's a bit more difficult. But remember, it's actually these bits that you're probably more interested in, actually trying to understand the way the method works. So here's how you use numerical recipes. The thing is about 1,400 pages long. It's enormous because there's all sorts of topics in there. You don't just read it from start to finish. The fact that it's got 4 authors tells you that probably they haven't read it from start to finish either. First of all, read chapter 1 because it's absolutely crucial to the whole thing, and especially about how numbers are represented behind the scenes inside a computer. So a couple of weeks ago, something came up about the epsilon machine, and I asked the room if anyone knew what machine epsilon was, and I got an awful lot of blank stares. That's something you should know. It's explained in chapter 1. Just to very quickly explain, it's the smallest number that you can add to 1 and get a bigger number representable by the computer. So very roughly speaking, if your computer represents numbers to 15 decimal places, and you try to do the calculation 1 plus 10 to the minus 100, the computer can't represent that number. It can't have 1.99 zeros and then a 1 at the end. It hasn't got enough decimal places. So if you want to know what's the smallest number I can add to 1 and actually get a different number, that's machine epsilon. If you didn't know that already, or you need a reminder, chapter 1. What you then do is you don't read the whole book. You find the chapter you're interested in, but start from the beginning and read up to the section you need. So if you need fitting data to a straight line, go back and read the introduction and 15.1 before you get to 15.2. So read the chapter beforehand as a general rule. That's generally good advice. There'll be something they rely on. Understanding the algorithm is more important than understanding the C++ implementation, unless you're actually yourself going to write a version of this algorithm. Maybe you are. And if you're going to write in C++, you want to understand the algorithm. The understanding the C++ is extremely useful because if you know how that works, then you've absolutely understood the algorithm. But don't get bogged down in the specifics of that specific language. Okay. So what I'm going to do next is go through the contents page, and there's a lot of stuff. All right, and a lot of it's just I've never needed it, and probably no astronomer's ever needed it. But there's some stuff that's just for other fields, even though it was written by 3 astrophysicists and 1 other guy. But I want to highlight some areas where you should at least have some idea of what that sort of code does, even if you don't know the exact method or it's slipped your mind. So first, we're just going to run through the chapters here. Firstly, there's that chapter 1. Read that, especially this bit, error, accuracy, and stability. The rest of it's, just have a skim. One of the most basic things you can do on the computer is linear algebra, anything with matrices, solving systems of equations, linear systems of equations with matrices. Hopefully you remember your linear algebra enough that you know that that's a thing to do. And again, there's all sorts of very complicated, very sophisticated, very quick routines here. But if you get sort of early on, 3 chapters into the 3 sections into this chapter, you'll have a rough idea of what's going on. And then you can just sort of remember that this stuff is available if you ever need to go back and look for it. So if you're reading something in a paper and it mentions that this was solved with Cholesky decomposition, the first thing you do is go, okay, is that in numerical recipes? Oh, it is. let me read up until that section and then I'll know what that is, if it's crucial for you to understand that. I should say, I have no idea what the Cholesky decomposition is, just so you know. Interpolation and extrapolation, crucially important. I think we use that all the time. All that is if I know the value of a function at a certain finite number of points, how do I find the value in between those points? There are some very basic ways of doing that. Cubic spline interpolation is one of the most important ones. Onto page 2, and doing it in multiple number of dimensions. If you've ever had to regrid some data to a sort of lower resolution just via interpolation, that's roughly the way that you would do that. So I think that's important. Being able to do an integration. I mean, there's things like the Simpson rule, which I at least learned in high school, maybe you did as well. There, again, are some very advanced methods here. If you ever get into a really chunky, difficult integral, but for the most part, just know that if you need to sort of get the area under a function, there are ways to do that numerically, which are fairly easy to understand. As long as you understand the elementary algorithms, if you need something more hardcore, you can always come back for it. Evaluation of functions is one where you can to skip over. It's not super duper important, but there's a nice little numerical details here behind how you actually evaluate a polynomial in a way that is most efficient. So you're not doing more multiplications, more calculations, more additions than you actually need to do. And I would also read this one on numerical derivatives. It's also a very nice illustration of why you need to know about things like the machine epsilon. The way that you calculate just the slope of a function, given some values of it, actually depends an awful lot on how the computer is keeping things behind the scenes. Never mind special functions. Things like cosine and sine integrals, someone's done that coding for you. Just use those like a black box, I would say. In particular, if you ever find that you need the hypergeometric function, I'd turn your computer off and slowly walk away. That function's just insane. Oh, all right. Random numbers, I think, is useful. Again, jump over to the end. Random numbers are extremely useful in a whole bunch of applications. It's useful to have some idea about how computers use that. Root finding is sorting and selection. How you sort a list is, I think, an opportunity for computer scientists to just show how clever they are at algorithms, but I don't think you actually need to know how it's done behind the scenes. That's just my opinion. I'll open it up for other people to have opinions. Root finding is just, I've got a function and it has a certain value. At what value of x does f of x equal 0? Which is actually quite a general problem. And again, once you get the idea of things like the secant method and bisection, the fact that there's more advanced methods is fine. You'll look it up if you need it. Minimization and maximization of functions. I would use that if you desperately need it, but not particularly essentially. Here's probably the most important set. The fast Fourier transform, right? You're in a lot of you do radio stuff. About most of us here, I think, do radio stuff. And a radio telescope is a big old fast Fourier transform machine of the sky. I think you need to know how that works, because not just how a Fourier transform works, but there is this algorithm called the fast Fourier transform, which is a form of magic as far as I can tell. It's actually genuinely impressive that it's as efficient as it is. So I think that section you need to get a handle on, especially if you're dealing with radio data. Basic things from statistics like means and average and all that sort of stuff. Are two distributions different? Will lead you to a lovely little thing called the Kolmogorov-Smirnov test. If you haven't learned that yet, have that one in your back pocket. This is the stuff that Nick was talking about, how to fit using least squares. A lot of the stuff about machine learning is in this chapter. Again, well, a sort of very basic beginnings on that. If that's something you do, get into that chapter, but otherwise, maybe not. I think being able to integrate an ordinary differential equation is absolutely like the alphabet of being able to do numerical computing. So just up to 17.1 and you'll be fine. I'll actually look at that stuff in a second. Boundary value problems are obscure. I don't think you need those. Integral equations are even more obscure. I don't think you'll ever meet one of those in your whole career. Partial differential equations, if you meet one of those, good luck. I don't think anyone's doing that. Nearest neighbor finding is the one section here that I think a lot of people might have seen in their work. So that's the final bit. So that was a lot of stuff. As if you're sort of in the long haul of starting like a PhD, or if any of that was completely unfamiliar to you, I think start putting aside a little bit of time to jump onto the Numerical Recipes website and just learn about, you know, one of those every now and then, and you'll sort of build up a set of a useful set of tools. Not only that, but the more of these you learn, the easier it will be to go back and learn some of the more advanced stuff if you need it at any particular point. Let me give an example of sort of numerical recipe, one of these algorithms in the style that Numerical Recipes does it. So ordinary differential equations. So the short story with an ordinary differential equation, if you have an initial condition, is I will tell you the way something changes and you come back and tell me where it is at any particular time. So you have an ordinary derivative, which is equal to some function of all the relevant variables in a certain number of dimensions. That's the setup of the problem. Usually the nature of the boundary conditions determine which numerical methods will be feasible. So think about, suppose the problem is how a projectile moves under gravity. An initial value problem is, you know, I shot the cannon at 100 meters a second at an angle of 45 degrees. Where does it land? A boundary value problem is, I shot my cannon from here and 10 seconds later, it landed 100 meters over that way. You know, what path did it take between those two values? So you set the boundaries and you try to fill in the gaps between. Initial value problem is, I know where it started, what happens next? Initial value problems are much more common and much easier to solve. The most basic algorithm for this is called Euler's method. So we have some equation. The way that x and y change is given by some known function of x and y. If y wasn't in this, then the way you would solve this is by doing the integral of f of x, and you would use those methods to solve this, not an ODE solver, almost certainly, because that if you can do it with integrals, do it with integrals. Do it with an ODE solver if you can't. So, you know, this might be the way that the projectile moves under gravity, and this is the initial conditions of I was at this point at this time and I shot it in that direction. So the way that you solve this simple version is to say, okay, I'm given this point, given this starting point, using this equation, I can solve for the derivative, which is the slope of this line. Okay, so given that information, my best guess for where y of x is at some time later or some other position, a step on, is to follow that straight line to here. And now I've got a value of y here and x here. I can go back to this equation, get the value of the slope again. There's the slope. So my best guess of where we go next is over here at y3. And repeat until you have some sort of solution. Now, they explain this method to then immediately explain that this is not the best method. But if you understand this method, you'll understand the later methods. So all it is, okay, I'm trying to trace out, it's a bit like, you know, the pirate's instructions to get to the treasure, right? From here, go in this direction, and then you take a step, and then it says, okay, from here, go in that direction, and you take a step. And that's the way you try and follow the instructions laid down by this particular function. So you could lay it out in code. Actually, I'll jump over that. What they want to show you next is what's called the Runge-Kutta method, after two Germans. Here's the idea. I take a half step and evaluate again on the half step. So I use Euler's method to take half a step to here. I calculate the value of the slope at the half step and then take that slope back to here and step along that direction, not along my original direction, if that makes sense to people. So go halfway, find out the slope halfway, and then go back to your original place and take a full step along the direction of the midpoint derivative. The reason that's better is actually this will be perfectly accurate if it can handle a curved line, is the short story, whereas the previous one could only handle a straight line. So again, you'll find code in there. We'll do this up. It's not actually that hard to understand. There's all the algorithm there to do it. I should say that all of this is perfectly useful. Asked myself the question a while ago, just for some fun. If you happen to be at a cricket ground and you hit a 6 in a certain direction, and then you move the same cricket ground and the same shot up to a higher altitude where the air is thinner, how much further would that cricket ball go under conditions where there is drag, where there is wind resistance? Now, we can easily write down that equation in Newtonian mechanics. We just can't solve it exactly. So I did all these calculations with a Runge-Kutta method, and this is the answer. It goes for at sea level, at the highest cricket stadium in the world, which is about 1,600 meters. It actually goes about 3 meters further or 4 meters further. So these are all very useful. This particular method is called a second order method. If you repeat this process a few times, you get a higher order method, and it's the most widely used one is the fourth order method. Let me finish off with the sort of homespun wisdom you get from Numerical Recipes. So here is their comment. For many scientific users, the fourth order Runge-Kutta is not just the first word on ODE integrators, but the last word as well. In fact, you can get pretty far on this old workhorse, especially if you combine it with an adaptive step size algorithm, where you change the size of the step as you go. Keep in mind, however, that the old workhorse's last trip might well take you to the poorhouse. Newer Runge-Kutta methods are much more efficient, and other methods can be even more efficient for problems where high accuracy is a requirement. These methods are the high-strung racehorses. Runge-Kutta is for plowing the fields. However, even the old workhorse is more nimble with new horseshoes. In the next section, we provide a modern implementation of Runge-Kutta, which is quite competitive as long as very high accuracy is not required. So that's the sort of homespun wisdom you'll get. It's not just here's a method, but here's its ups and downs and when it's useful or not. So that is Numerical Recipes, which is widely used, highly respected. It's not perfect. No set of methods can be. It's now 15 years old, but it's still very good for learning the sort of basic methods that you see around the place. All right. Ta-da. Any questions? Just a massive dump of information for everyone. Hit it. The other staff members or other people or senior, do you agree with my which sections are useful and which ones aren't? Or
well, since you mention it, I just I would certainly back you up on Kolmogorov-Smirnov when I ran into a reference to it in the end of my PhD and went and read it in Numerical Recipes. It was then a big chunk of my PhD. It's suddenly, oh, I can do that. Because the wonderful thing about Kolmogorov-Smirnov is that it works on unbinned data, and therefore you can use small sample sizes. Anybody who's working on EMU doesn't care about KS because you've got a million galaxies. Anybody who's working on an old-fashioned sample where you've pat yourself on the back for getting 30, Kolmogorov-Smirnov is great. I would also probably the disagreement I have is that when I was talking about line fitting or fitting functions, a lot of the stuff you really end up using actually ends up, so all the stuff around nonlinear models, even general, particularly nonlinear models, actually uses all the minimization stuff, which you skipped. So all that stuff around downhill simplex and all that lot, that becomes important. once you start doing nonlinear fitting, and a lot of things are nonlinear. So that's my disagreement. Oh yeah, also for observational people, probably if you're really unlucky, you will actually need to learn about Bessel functions and spherical harmonics, but only if you're unlucky.
I think you need to know about those functions. I don't think you need to know the details about how to calculate them.
Oh, good heavens, I hope not.
Yeah, so behind the scenes, there is some algorithm in your computer that calculates like the sine of x and the cosine of x. Like I have no idea what that is, and I don't really care. Right? I'm not. If you need to calculate those functions, there's some, the actual algorithms you use are there. I don't think you need those, but sometimes you do need to know what those functions are. Yeah. I denied a lot about minimization and maximization, I have to say. I guess, I don't know, at least know those algorithms are around. Like I said, if something comes up, go see if it's in numerical recipes, and that'll be your best hope of someone explaining it to you in a way that is not either ridiculously oversimplified or just entirely mathematical jargon.
Yes, actually, just to with the example that I gave when in my talk about fitting in my thesis, when I was fitting this function to skydips, what I actually used numerical recipes for was that it turns out the function was written. Somebody had already written it in Fortran. It was implemented. Everything was fine. I wanted to get an uncertainty out, which they weren't giving you. So what I actually used numerical recipes for was that I used numerical recipes to understand what they had done. And then you realize that if I grab this thing out of their code, that basically gives me the uncertainty. It gives me the confidence interval. And so I use numerical recipes to understand what somebody else had written. And then it turned out that all I had to do was grab a variable and print it out, and I was done, which is kind of nice. But yeah, that's what numerical recipes is good for. Because, the person who wrote the software in the first place probably used numerical recipes.
Yeah, I mean, to me, it seems like Python is really the killer of this this big book, because I mean, when I was a PhD, we program everything with C, and then you find that with the GNU Scientific Library, it's so difficult to use. It almost certainly doesn't work with your problem or your data. So you have to go to the numerical recipe and write your own codes. But nowadays, because Python libraries are so easy to use and so flexible, you don't need to actually go back to numerical recipe anymore. So I think the way of actually programming is different now. You used to actually write codes to solve your data or suit your data. But nowadays, somehow you modify your problem or your data in order to work with the Python library. So I think it's actually very different nowadays. But
bear in mind that the chances are the Python library you're calling is a Python wrapper to a C or a C++ library, because otherwise it will be slow. And that C or C+ library was almost certainly written by somebody who had numerical recipes next to their computer and was typing away at it. So the chances are that the Python library you're using is probably numerical recipes is probably the best manual you'll get as to how it actually works.
Yeah, but I think
what's going wrong with it.
Yeah, the interface of Python is much better, so that you don't need to go back to. So
where you used to just type out what they did in Fortran and compile it, these days you just go find the Python library and run it.
Yeah, so numerical recipes is a little bit of a relic of a time when it was all we had. It was either this or try to understand some, as she said, some really complicated stuff written in C behind the scenes in a science by who knows who didn't explain what they did, and maybe there's comments or so. Look, if you've got something and it works and you sort of have a rough idea how it works and that's fine, then good. If you find yourself, if there's if someone uses a term in a paper and you don't understand it, and it's obviously some sort of numerical algorithm and you need to learn what it is, numerical recipes are very good for that. Again, as I said before, maybe not for the code, because someone's probably written something already that does it. But as Nick said, if you need to get in behind the scenes and know what they've done to open up the bonnet of the car, see how it works, then again, this is one particularly good resource. All right. I've recorded this. It's now, it should be on my computer or online or somewhere. We do need to do something about where we put these recordings. So let me try and sort that out. I think we might be able to make ourselves a little views site and then put them all there.
Or you can get a you can get a shared box on Cloud Store.
Yeah,
they'll usually set up the team and they'll usually give you like a terabyte or something.
Okay.
If you ask them nicely.
The other thing is most people have done the doodle poll about when they're free. So if you haven't done that, please do that. And I'll let you know in the next day or so who wins the lottery of when we do Journal Club for this semester. Otherwise, I think that's about it. Thanks, everyone.
Thank you. Great talk, Luke.